the vector algebra of displacement. If we learn physics, especially if we study Newtonian mechanics, we assume that space is homogeneous and isotropic. This is a strong requirement of the Euclidean space. In fact, we don't know whether we are living in a Euclidean space or not. The only thing is that we have never have found a counterexample. Once you find a counterexample, then you have to modify the postulate. Around 100 years ago, Einstein's relativity revealed that our space is not a pure Euclidean space. Instead, it is a Minkowski space. However, if we restrict ourselves within a region where particles' motions are restricted to have a very tiny velocity whose magnitude is much, much smaller than the speed of light, then it's fine to admit the assumption that the space is Euclidean. Euclidean space you learned for a long time from elementary school, and the special nature of the Euclidean space is to satisfy the Pythagoras theorem. To have a Pythagoras theorem, or even before you learn from elementary school a number line, 0 and 1, and you identify the one-dimensional Euclidean space as a one-to-one correspondence between this number line and physical straight line. So there is a mapping. We choose some point origin and some point A, and you identify the origin of first the reference point to be 0. And another point, whatever point you may bring from a straight line, this suppose that this is A, then you identify this point to be 1. And everywhere, whatever point, whatever else point, suppose you have chosen P, then there is a real number. And this real number is assumed to be unique. Okay, so this is the nature of the displacement in one-dimensional Euclidean space. And we identify real number with the position of a point on a straight line. That's it. However, there is a big assumption that any distance of, for example, unit distance, suppose we have 1 centimeter in here, then this 1 centimeter is always the same under any kind of translation. Okay, 1 centimeter here and 1 centimeter here, they should be the same. This kind of thing is called homogeneousness. The number line is a uniform. It is a very simple idea, but in reality, in many times, space is not homogeneous. So homogeneous space is allowed only if the space is empty, and everybody knows that except for the space between the sun and earth, everything is filled with matter. In addition, even though in a vacuum, electromagnetic fields are completely filled in, so it is all virtually impossible to have an empty space in reality. But mathematicians has a very, they had their own imagination. For example, Galileo's, the Newton's first law is called the law of inertia. So nobody can imagine such kind of law of inertia because we are living in a space with full of frictions. However, he was able to find a very nice postulate, law of inertia. This is realized only if we erase all of the matter in the universe. Anyway, so we assume, and Euclid assumed the space is homogeneous. In addition, there is another assumption: the space is isotropic. Isotropic is very similar to homogeneousness. Instead, it also considers a direction. In one-dimensional straight line is covered by a number line. It has a two orientation, forward and backward. So adding +1 to shift the point to the right is the same as adding negative value, the shifting to the left. This distance is the same. Forward and backward is the trivial idea. However, this equivalence of two directions is called isotropy. What happens if we extend the space into two dimensions, and then you can draw a circle, and the circle of radius r is a symmetric invariant on the rotation. If you rotate this circle, whatever angle about this z-axis, then this circle is the same always. So this is a rotational invariance of a circle that is based on the idea that space is isotropic. Okay. Parameterize a point P on a straight line connecting two points in space. And these numbers are called the Cartesian coordinates. You should be, all of you, except for a few, should be familiar with at least ordered pair x comma y. Comma z is some extension to the three-dimensional space. So if you want to express a point in the three-dimensional space, you need three numbers that are called components. The x component, y component, and z component. We have 2 points. We go to the middle school again, and there are 2 points, and we are parameterizing a single point on a straight line. Euclidean geometry says we can draw a kind of right triangle, and all of the right triangle with the same angle are similar. Using this linear relation, we can construct this very simple parameterization for a point on a straight line. That is, we choose a point from, suppose that we have origin in here. To arrive at this point, you first go ahead to arrive at point A, and then from A to B, we choose this is a new origin and new point A prime. So what happens if we choose this, allocate a real number 0 for this point and real number 1 to this point? Then, because of this linear relation, I can always find a point P between or outside of this straight line connecting A and B in this form. Go to A first, and then B minus A is the vector B minus A. This is B minus A. So from A to B. So B, this is the kind of, if I write this one as a B vector, and the a vector, then this is the vector b minus a, something like that. Multiply a real number ranging from 0 to 1, then if you insert the 0, you will obtain a. If you insert 1, you will obtain b. If you insert a number greater than 1, then that point should be somewhere outside. If you insert a number less than 0, then that point will be somewhere around here. So point P on a unit circle, this is a unit circle. Unit circle means radius is 1. Centered at the origin, okay, center is at the origin, can be parameterized by this. Yes, everybody knows that this is 1, so cosine and sine, that's fine. And middle school students know the tangent to the circle at point P. This is a unique straight line, and there is a single point that touches the circle, and they know, middle school students know, this is right angle. And if it is a right angle, and you know how to draw a congruent triangle in here, okay, so this length, the same, this length, the same. Okay, so xy coordinates are exchanged and x coordinate is negative. So middle school students can compute this coordinate. And this coordinate shows the slope of this straight line that is perpendicular to this straight line whose slope is tangent theta. Using this, even though some students do not know how to compute the derivative of cosine and derivative of sine, the middle school students' knowledge is used to compute this derivative is cosine's derivative minus sine and sine's derivative of cosine. The explanation in detail are given below. Okay,